So we're still talking about root finding problems, and I'm going to move on to sort of the general category of fixed point iterations for doing root finding problems, which you can build lots of different methods in this category. Newton's method will fit in this. I guess what's nice here is that you kind of have one theorem that says if the method has these properties that are relatively easy to check, hopefully, then you know it converges. So you can apply this quite broadly. So fixed point at iterations. Okay, so again, we're trying to do root finding problems. So we want to find alpha, the root, such that f of alpha equals 0. Okay, and in this approach, we try to find a new function, g, such that not only is alpha a root of this guy, alpha is a fixed point of g. Okay, so we find some function g, okay, such that, say, alpha is a fixed point of g. And that means that if I plug in alpha, I get alpha coming back out again. Okay, and why is this a nice approach? Because it gives us a really easy way to build a numerical method from here. So now what are we going to do? We're going to say, let's start with a guess, xn, and we want to try to make it better. So what am I going to do? I'm going to iterate like this. Xn plus 1 equals g of xn. And what's our hope? Our hope is that if we've picked g in a good way, this converges. And if this converges, then as I put things in, xn isn't going to change anymore, right? That's what should happen if this converges, that I put in xn, I get basically the same xn plus 1 back out. And if that's the case, then I should have in my hand a fixed point, right? Put the same x I put in, I get back out. That means a fixed point, and that means that I've actually got my alpha. So this is the approach that we're going to take. And there's, for a given f, there's lots of ways of building fixed point iterations. Some of them may be better than others in terms of numerical properties. So if we just take as an example a simple quadratic equation, for which in real life you're probably not going to use a fixed point iteration to solve this, obviously. But it's kind of illustrative. So how do we build a fixed point problem out of this? Well, what we've got to do is somehow get x on one side of the equation, right? And whatever is on the other side of the equation becomes our g. Right? So there's lots of ways to do it. The easiest way would be maybe to move this x over, right? And say, well, we could have x equals x squared minus 2. Okay, so my g becomes x squared minus 2. Right? That's a fixed point problem that would have the same root as this equation. Now, whether it's a good method or not for iterating, we don't know yet, but it's certainly a fixed point formulation. We could do other things. We could say, let's put the x squared on one side of the equation. Okay, and then maybe we decide to take a square root, and we decide to take g of x equals root x plus 2. Or we could have tried g of x equals minus the square root, right? That would have given us another fixed point method that might not converge to the same root. Or we could do more sophisticated things. So I could say, let's see, x squared equals x plus 2. It's x plus 2. How do I want to write this? And then another way to solve for x here, before I took the square root, I could simply divide both sides of this equation by x. So I could say, well, if this is true, then x equals 1 plus 2 over x. Right? And now this becomes my g. Or what else? I could manipulate this in crazy ways. I could say I want this to be equal to 0. I could divide both sides by anything or multiply both sides by anything, and it should still satisfy, this equal to 0. So I might say, let's have x squared minus x minus 2 over, say, 2x minus 1 equals 0. That's still not looking like a fixed point method, but you can always get something to look like a fixed point method by just adding x to both sides. Right? So I could say x plus this equals x, or x minus this equals x. So for example, I might decide to go x minus all of this is equal to x. And now, again, this becomes my g of x. And this is Newton's method, exactly. So this wasn't actually a crazy manipulation. This is to show you that Newton's method, right, really is a fixed point formulation of this root finding problem. So if we can come up with a kind of really simple general technique for analyzing methods like this, right away we could analyze some of the methods that we've done so far, like Newton's method, maybe like the secant method, right? And the idea is you do all the work once, and maybe it's messy once, but then you can apply it very easily to test lots of different methods and see do they converge or not. Okay, so let's see what happens. Let's first of all say, this is the picture of fixed point. I'm going to do a lot of these. So I'm going to do some little theorems today. And I'm going to do the proofs two ways. One is the rigorous picture proof, where I'm just going to draw a picture that hopefully convinces you, this theorem looks right. And then we'll do the actual rigorous proof. But pictures are great for gathering intuition to give you an idea how you're actually going to go about your proof, or what you expect to be true. So say this is my function g. Okay, so for the fixed point, we want g of x equal to x. So I'm going to draw a second function, the line y equals x. Okay, so that's this line. This is my y equals x line. And the fixed point happens right here where these two cross. Okay, so this right here is going to be my alpha. And the height here will be g of alpha, which is also equal to alpha. Okay, so we want to know a few things about these fixed point methods. One, I guess we'd like to know, if I write down a problem like this, is there actually a fixed point? Right? You can imagine I could draw a curve that's just down here and never actually crosses the y equals x line. So if I said, solve this fixed point problem, well, it's not well posed, right? It doesn't have a solution. Secondly, life is probably better for us if we have a unique solution, right? Obviously, this guy right here doesn't have a unique solution. This guy probably does have a unique solution when we look for a fixed point of it. So we might build a fixed point method that picks out a particular root, for example. Okay, so here is our existence and uniqueness result. Again, I'm going to write down the result first, and then we'll draw some pictures and actually prove it. So here's the theorem, 2 parts. Okay, so let's start with a g that's at least continuous. So it's a continuous function on some interval from a to b. And the values of g don't get too out of control here. So the values of g on this interval are always going to live in the same values. The value of g never goes below a, it never goes above b. Okay, that's enough to guarantee the existence of a fixed point. So g has a fixed point. Okay, and then secondly, we want to know what it would take to make this unique. Continuity is clearly not enough to make this unique, because I could just have a g that just wiggles around this line, or it could even just, maybe g of x is actually equal to x, this function, and then everything is a fixed point. So this is not enough for uniqueness. If we want uniqueness, we need to control the derivative a little bit. Okay, so I'm going to say if in addition to the above, the derivative exists. Greater than 1? Close. So we actually want it to be less than 1 in magnitude. And again, I'll draw you a picture, and as soon as you see the picture, you'll say, oh, that makes sense. So if additionally G prime exists on this interval, and there exists some constant, and the constant should be between 0 and 1, okay, such that the magnitude of G prime is always bounded by k. Okay, so G prime is strictly less than 1 everywhere. Okay, if this is all true, then the fixed point is unique. Okay, so let's try to prove this. Again, we'll do this in a couple different ways. So let's do the proof of A first of all. All right, so first of all, the picture proof. So what have I got here? I've got a box. So my domain that I'm looking at is A to B. Okay, and whatever our G is, we're going to be interested in when it hits this line. Yes? Can I move the chair? I can do that. Yeah, don't be shy to ask questions like that. Everybody on this side of the room is probably wondering the same thing. Okay, so we want the values of G, or going to require the values of G to stay in this box between A and B. Okay, so we know that A is right here, and we know that B is right here. Okay, so we're stuck inside of this box. And I've got a continuous function. So my continuous function, G, if I look on the left, it has to start somewhere. But maybe it starts touching the line and we've automatically got a fixed point, or otherwise it starts above the line somewhere. And when we get to the right, again, G has to live somewhere in this box between A and B. If it lands here, then we've already got a fixed point here, and otherwise it's somewhere below it. And now I've got to draw a continuous curve that hits those two values, right? It's got to cross this line somewhere, right? As long as it's a continuous function, it has to cross this line. And if it crosses this line, then I've got my fixed point. So what's the mathematics of this? Can you guess what's the theorem from analysis or calculus that I would use to prove this? Intermediate value theorem, exactly. Okay, so let's let h of x equal g of x minus x. Okay, now what happens at x equals a? H of a is equal to g of a minus a. Okay, and this is greater than or equal to 0. Right? It has to be, because g is never allowed to be less than a. We've required that up here. So this is certainly bigger than or equal to 0. If we move to the right, g has to be less than or equal to b. So this is less than or equal to 0. G is continuous, which means h is continuous. So the intermediate value theorem is going to say, well, there exists some value alpha in here. Okay, such that h of alpha hits 0. And if h of alpha hits 0, that means g of alpha minus alpha hits 0. So that means that g of alpha equals alpha. Right, so a nice, really simple little proof that the fixed point exists. You're happy with that part? Okay, it exists. So now let's try to convince ourselves that it's unique if we add in this extra condition that the derivative is strictly less than 1. Okay, so part B. Okay, again, I'm going to draw my box that g stays in. There's my line y equals x. Okay, this line has slope 1, yes?
Yes.
Yes, okay. So g starts over here somewhere, and eventually it crosses this line. Now, we want to know, is it possible for there to be another fixed point? Can it catch back up with this line and cross it again?
You have to analyze the second derivative.
We won't even have to analyze the second derivative. So what's happening here? This line is traveling up with slope 1.
Right.
This line is traveling, well, either up or down, but with slope less than 1, right?
Right.
So it's always going up with slope less than 1. This is always going up with slope 1. This curve is never going to be able to catch up to this curve, right? So since this slope is less than 1, it can never catch up with the line y equals x. Okay, so let's try to do this a little more rigorously. Do you know what the first step usually is in a uniqueness proof? Assume you don't have uniqueness. Okay, so this is something that you can file away for later, other proofs you do. When you want to prove uniqueness, the first thing you do is assume actually there's two solutions. So let's assume there are two fixed points. Okay, we'll call them P and Q. Okay, and P and Q, let's specify, they both live in this same box, right? Because we haven't said anything about what might happen outside of this box. Okay, now what do we need to do? We need to bring in derivative information somehow. So what's the easiest theorem that will bring in some derivative information that will compare what happens at these 2 points? Mean value theorem, yeah. So the mean values theorem says, okay, well, there exists some point in between P and Q, and certainly in between A and B. Okay, such that what? The derivative at this point is equal to the slope of the secant line connecting these 2 points. All right, so g of P minus g of Q. Oops. Call that a G, or P minus Q. Now, we've assumed something special about P and Q. We've assumed they're fixed points, right? And that means that if I stick P inside this function, I get P coming back out. And if I stick Q inside, I get Q coming back out. So this is P minus Q divided by P minus Q, which is 1. And that's a problem because we assumed G prime can never be 1. It's always bounded, it's always less than something that's less than 1. So it's a contradiction. So this is our contradiction. Okay, since we know that G prime is less than 1. And then we say, great, the fixed point is unique.
a larger statement we can make that has to do with the concavity of the function?
Is there a larger statement we can make that has to do with the concavity of the function? I guess what's the larger statement that you want to make?
I'm not quite sure.
Okay.
That's the same question I was asking before, the second derivative, but
So I'll say, and we'll see this actually in a little bit when we get more into order of convergence. The higher derivatives, what happens with the higher derivatives can affect how fast the fixed point method converges. So maybe I'll just ask you to hold on to that thought for a little bit and we'll come back to that. So yeah, higher order derivatives can be important. They're not needed just for these sort of simple statements.
So why wouldn't have the statement that G prime has to be greater than 1 work in this scenario? It's because we wouldn't guarantee G cross the line.
Why wouldn't it have worked for G prime to be greater than 1? Yeah, so what was important here, right, was really the fact that G prime never hit 1. So you're right, that would have worked. We would have had kind of, where's my picture? We would have had the opposite problem here, is that we come up with a steep slope, right, and for it to turn around and come back down here, the derivative would have to get less than 1. So that would actually work here. Where we're going to find it isn't going to work is that when we try to build a fixed point iteration out of that, it's not going to be a convergent fixed point iteration. So yeah, it's a good observation. With this theorem, the conditions I've given are a little stronger than we need for this theorem, but they're exactly what we need for actually analyzing the numerical method. We happy with this otherwise? Reasonable? Okay, so let's try to analyze a numerical method then. Okay, so we've figured out how to decide if a fixed point problem looks well posed, but can we solve the problem? So again, I'm just going to start with a couple picture examples of what a fixed point iteration looks like it does, and we're going to try to figure out from the pictures what are reasonable assumptions to make. So will a fixed point iteration converge? Okay, so always need this line y equals x. And I'm going to draw some g of x here. And I'm going to come up with some kind of initial guess over here. So this is my g. This is my y equals x line. Here's my initial guess. And let's just try to picture what a fixed point method does. So the fixed point method says, okay, we come up here. Take x naught, we plug it into g, and we say, okay, this is g of x naught. Now, we're going to let this value of g of x become our new x value, right? So we want to find the value of x that has the same y value as that. That's the same as projecting over to this line y equals x. So we say, when is x equal to this y value? Well, it's exactly here. Okay, so that's what the method does. And then we'll come back down. This becomes my x1. Okay, and then we do the same thing. I say, okay, let's compute g of x1. This is going to be my new x value. So I'm thinking of it right now as a y value, but I want to take it over and actually find the corresponding x value. And again, I just take it over to this line y equals x. And I get a new guess at my fixed point. And this looks like it's working, right? This looks like it's walking us over towards this fixed point. Okay, I'll take another example. Okay, I need my straight line. And maybe I do something, a g that looks something like this.
question.
Yes?
So, would you, well, would, never mind, I'll let you do it, because you're going to say it.
I'm going to say it, okay. I don't need to be here to teach. You guys know what I'm going to say before I say it. We can all go home.
That's fine.
All right, So let's try this again, and let's start with an x naught, say that's over here. Okay, and I'm going to do the same thing. I come up and find that g value. And I say, well, now I want to make this my new x value. So just like before, I got to project over to this line. And I get a new x value. Okay, I want to update it, so I come up to g. I need to project over to this line, so I project over to this line. And I get a new x value. Now this doesn't seem like it's working quite as well as the last time. The last time we kind of just marched over here towards the fixed point. This time, okay, we're bouncing back and forth, but it looks like we're bouncing farther and farther away, right? So what's the difference between these two pictures?
The absolute value of the derivative is greater.
The absolute value of the derivative is bigger than 1. So this comes back to Jake's question, right? Could we let the derivative, force the derivative to be bigger than 1? Yes, for the uniqueness theorem, but no for the fixed point iteration. Having the derivative be bigger than 1 is going to effectively bounce us farther and farther away. Okay, that's an observation from 2 pictures. Observation from 2 pictures is not a proof, of course. So let's try to do this rigorously. Okay, so again, I'll write down the theorem. You basically already have all the information you need to write it down. It's the same hypotheses that we had before. So let's let g be a C1 function. Okay, we care about derivatives. We know we care about derivatives here. Okay, with g of x taking its values between a and b for all x living between a and b. Okay, and again, there exists a constant k such that g prime of x is always less than or equal to k, which is less than 1. Also on this same interval that we care about. Okay, so now I want to use this to build a fixed point iteration. I should obviously start with an initial guess that lives in my window, right? Because we have no guarantees of what the function is going to do outside this window. So let's choose any x naught that lives in my window. And then we do this iteration. Xn plus 1 equals g of xn. Okay, and now I claim this works. Then this converges to the fixed point of g, right? The unique fixed point of g that lives within this window. Okay, so let's try to actually prove this. Okay, what's one thing we care about? So we cared about this when we analyzed Newton's method last time, right? We had this little interval with delta, of radius delta, and we cared that Newton's iteration kept us inside this same interval. So similarly, we should care about that here, that we start off in this box between a and b, and the fixed point method better keep us inside this box. Okay, well, let's write it like this. We know that if xn happens to live in this interval, then xn plus 1 is nothing but g of xn, right? It automatically lives in this interval too. So we're good there. So iteration will certainly keep us in this window. You know, whether it will move us towards the fixed point or just bounce us around forever, we don't know yet, but we'll stay in the window, which is good. We need to stay in the window to use the estimates we have on the derivative, for example. All right. Now, the other thing we usually are going to do when we're analyzing these things is basically look at our error, xn minus alpha, and we want to try to make sure that's going to 0. So if I look at xn minus alpha, all I'm going to do is start writing down things I know. We should build in what these things, how these things are defined, right? So this xn was defined through our method. We better bring the method into the analysis somehow. Okay, and alpha. Alpha we know is a fixed point, so this is equal to g of alpha. What's that?
I was going to say to the P or
To the P? Oh, I haven't. What is P?
the order of conversion.
Okay, so we're not even looking at order of convergence right now. We're just trying to figure out, does this actually converge? We will do order of convergence also. I promise you we will get there. So what have I used so far? I've used the information that G stays in this window. I've used the definition of the fixed point method. I've used the fact that alpha is a fixed point. What information do I still have that I haven't used yet? The derivative. All right, so how can I feed the derivative in here? I can, linearize or kind of equivalently.
You can divide by those 2 points.
I can divide by those 2 points. Yeah, you're both saying the same thing in different words. Or in other words, I can do mean value theorem, right? To get an estimate of this in terms of the derivative and the difference between these 2 points. So indeed, the mean value theorem says there exists some value, xc. Let's call it xn minus 1, such that g prime at this value, right, is equal to the rise over the run. Okay, so that lets me rewrite this error a little bit. So if I do that, I have xn minus alpha is equal to the magnitude of g prime times xn minus 1 minus alpha all right, g prime, I don't know exactly what value g prime is, but the key is that I have bounds on it, right? It's certainly never going to get bigger than k. So this is bounded by k times xn minus 1 minus alpha. Right, this is how a lot of these convergence results are going to go. We look at our error. We try to get it in terms of the previous error, right? And this works for any value of n, right? This works for n equals 1 or 2 or 3 or anything, which means that I can keep using this result. So I can say, well, let's keep marching back in time. And I can put this error in terms of its previous error. Right? And I can keep going. I can go all the way back to x naught. So when I had an n minus 1, I had k to the 1. When I had an n minus 2, I had k to the 2. So I'm going to have k to the n, yep. X naught minus alpha. And now, of course, I care what happens as n goes to infinity. So if I want to look at my error as n goes to infinity, Well, it's going to be bounded by whatever this does is n goes to infinity. This part doesn't depend on n. And it's 0 because k is less than 1. So this is the part where it mattered that the derivative was less than 1. Okay, so since k is actually positive, the way we've done it, since k is less than 1. Okay, and that means that indeed xn converges to alpha. Looks okay?
Yeah.
Questions about this?
For the mean value theorem,
Yes.
you have xn minus alpha, but you have xn minus 1 minus alpha.
For the mean value theorem. Yeah, so I guess I was using the mean value theorem to be able to simplify this part,
Yeah.
right? No, the mean value theorem applies just as well to xn minus alpha. I would just get a different value of c coming here.
But it's implied that that's justified by the fact that both of those lie between A and B.
It's justified by the fact that these things all live between a and b, yes.
Cool.
Yeah, so it matters for all this argument, to be able to use it, it matters that we live between a and b. So that's why my first line was to check, do we actually live between a and b? Any other questions? All right, it converges, so we want to know next how fast it converges. So I'm going to let you think about that for a second, actually. What do you think the order of convergence is of a general fixed point method that satisfies these conditions? Linear, okay? Any other guesses?
More than
Not more than linear.
Superlinear, maybe?
Maybe superlinear.
Isn't Newton's method a type of, well, no, that's
Okay, isn't Newton's method a type of fixed point iteration? Sure it is.
so.
So, so you're thinking maybe quadratic is a possibility. Okay, so I guess you're all right to an extent. It depends on the fixed point method. So let's just start with a general fixed point method. All we know is what's here. What's the best we can hope for?
Linear.
Why linear?
Because it's the factor is by a constant. Every iteration, the distance between like the iteration and alpha.
That's right. So when I look at my new error versus my old error, right? So I didn't try to do anything fancy. I just said what comes out naturally. What comes out naturally is that we get something that's bounded by a constant times the old error, right? And that means that this divided by this is going to somehow limit to a constant. But that sounds linear. So we can, again, write this before. You know, as long as G prime is continuous, which I assumed here, we had that xn minus 1 minus alpha was equal to G prime of, xn plus 1 minus alpha is equal to G prime of Cn times xn minus alpha. We already did this. And what we need is the ratio of these two things. So the limit as n goes to infinity of xn plus 1 minus alpha over xn minus alpha which is the limit as n goes to infinity of G prime at Cn. Okay, what is this limit equal to?
It's bound by a constant less than or equal to k.
Okay, it's bounded by a constant less than or equal to k. Can we make it more precise?
Less than 1.
Okay, it's less than 1. What else? Well, let me rephrase. What does Cn approach?
Or alpha.
Cn approaches alpha, exactly. So when we bring in this Cn, right, the Cn from the mean value theorem is actually going to live between these 2 points, between, as I've done it there, between xn and between alpha, right? But Cn is sandwiched between xn and alpha. Xn is approaching alpha as n goes to infinity. So Cn is sandwiched between an interval that is closing in on alpha. So this indeed will be nothing but g prime alpha, right? Since Cn is between xn and alpha. And we already know that xn is going to alpha. And what else do we know? We know that g prime is continuous. Okay, so this in general is indeed linear convergence. Okay, but we observed we don't always get linear convergence in fixed point methods. Sometimes we get quadratic convergence, like Newton's method. So what would have to happen in order for us to get higher order convergence, do you think? You can kind of look at the analysis. Where would this change so that we might get something better than linear?
G prime squared
Okay, so we certainly know that for, say, quadratic convergence, right, we would be looking at the ratio of this, the new error to the old error squared, right? Now, right now I'm just looking at the ratio of the new error to the old error. Yeah.
Does that involve the second derivative at all?
Does it involve the second? So you're close. It involves derivatives, yeah? So for linear convergence, what did we say? We said the new error is kind of not much different than the old error, right? It's just a little bit smaller. For, say, quadratic convergence or superlinear convergence, we said actually the new error is quite a lot smaller than the old error. So what do you expect this ratio to converge to if the new error is really a lot smaller than the old error?
0.
You might expect it to go to 0, right? Actually, so this is what you do in one of your, or are doing in one of your homework problems, is you're saying, right, this ratio of this new iteration to the old iteration converges to 0 because this new one, the error, is getting small so much faster. Okay, so if we want this limit to be 0, what should we expect for our g?
To be a constant? Oh, no, sorry.
G prime of alpha is 0. So if we want superlinear convergence, we've got to look for a fixed point setup where G prime of alpha is equal to 0.
For that particular case, can we say that the function have multiple roots?
Can we say that the function has multiple roots? So it would have, I guess, not multiple different roots, but a root of multiplicity greater than 1, right?
Would our interval have to be, that means our interval of convergence is smaller, yes?
Does it mean that our interval gets smaller? So this doesn't really say anything about how our interval changes, right? It's still the case as long as G stays between A and B in its values, we're still in good shape.
Like for the bisection method, like the interval of convergence is in the entire real line, but the Newton's method is like it's limited, right?
Yes. So what's going to limit your interval is that we're trying to we need to shrink it enough that we can guarantee that G never gets less than A or bigger than B. So we might have to shrink it to make that true. It might be also the case that near our fixed point, g prime is less than 1, but eventually g prime gets bigger than 1. So that's what's going to shrink our size of our interval. The value, asking it to take a particular value at one point isn't really going to affect the size of the interval. But certainly, hopefully this conclusion makes sense. If we want superlinear convergence, okay, we should expect g prime alpha to be equal to 0. Okay, so let's justify this rigorously and say what order of convergence can we really get here, depending on g prime alpha equal to 0, or maybe even higher derivatives are equal to 0. I think was it you that asked what about higher derivatives? Well, maybe the more derivatives we get equal to 0, kind of the farther we can push this. So let's try to justify that. Let's suppose that maybe g prime alpha equals 0. And maybe g double prime alpha equals 0, all the way up to, say, the kth derivative of g is equal to 0. Okay, I'm going to need some, to look at these higher derivatives, obviously they need to exist at this particular point. It's not going to surprise you, we need to assume a little bit more than that. So we need to assume something about continuous derivatives. So what happened here? It was the first non-zero derivative here that basically told me my order of convergence, right? So for linear convergence, we expected g prime to be not 0, and we needed g prime to be continuous in order to push these limits through. So I'm going to assume these are 0, and then my next derivative is the non-zero one. I'm probably going to need it to be continuous to make these limits go through. So let's suppose that gk plus 1 is continuous. Okay, so before we used, people suggested different things that were equivalent, linearized mean value theorem, whatever, to get this problem in terms of the derivative. The generalization of all of that is that we're going to use Taylor's theorems to bring in these higher derivatives. So we should expect that we're going to need to know this. Okay, so we're going to bring in these higher derivatives, do our kth order Taylor expansion. So I have 1 over I factorial, the ith derivative at alpha times x minus alpha to the ith power. And then I have an error term, and the error term is important. K plus 1, yeah. So the error term always just looks like the next term in the Taylor series, with the exception that I don't exactly know what value I'm plugging in here. So this should be k plus 1.
Oh, sorry.
Yes.
I should have asked this earlier. This is just it just relates to Stafford theorem.
Okay, let's go back.
Isn't that the condition for Lipschitz continuity?
Isn't this the condition for Lipschitz continuity?
Yeah, for G.
So, I mean, G prime doesn't have to exist in order for it to be Lipschitz.
Oh,
so
right.
it's very close to the condition for Lipschitz continuity. But what I wouldn't be able to do is make this kind of argument if all I have is Lipschitz continuity.
Oh, right.
All right, so we can simplify this a little bit. Taylor expanded. This alpha is special. right? Alpha is my fixed point. So this is equal to alpha. Alpha was special for this particular choice in that all these derivatives were 0. Right? So all of these are actually 0. So what I really have is alpha plus this error term. Okay, so that's for the function g. Now we're going to feed this into our convergence analysis. So what are we doing? Our convergence analysis, of course, we look at xn plus 1 minus alpha. And we say, well, this is the usual thing. We say, where does this come from? Let's plug in the method to see where it came from. It came from g of xn. And now we can estimate all of this, right? Just like we did before. Last time we did it with mean value theorem. This time we're going to use the Taylor's theorem. So g of xn minus alpha just leaves me with this leftovers. So I have 1 over k plus 1 factorial. G, k plus first derivative evaluated somewhere, times xn minus alpha to now the k plus first power. So you look at that and say, what order of convergence do I expect here? K plus 1, exactly. So, right, I didn't do anything magic or I'm not making wild guesses at what value of p is going to work as my order of convergence. It fell out here. Okay, so we look at this ratio. X minus alpha to the k plus 1. And we say, well, this, again, Cn is going to approach alpha, just like it did before. I made the assumption that this k plus first derivative is continuous. Because we guessed that we'd probably be trying to pass this thing through a limit. So what do I get? I get 1 over k plus 1 factorial times the k plus first derivative evaluated at alpha. Okay, so what do we get? We get order k plus 1 convergence. Okay, so if only the first derivative was 0, right? The case derivative was 0, then we'd expect a boost up to 1 plus 1 convergence, second order convergence. If we could manufacture G to make higher order derivatives 0, then we could boost this even higher. Looks okay?
Is it okay to assume that the higher k plus 1 is, like the smaller that term is?
Is it okay to assume that the higher k plus 1 is the smaller this term is? That's a good question. It actually will become somewhat of an important question when we get to interpolation. The answer is no, because obviously as k gets bigger, this term gets smaller. But all I've said is that these derivatives are continuous, but they might be very large. And it's possible that g is small and g prime is not too big, and g double prime gets pretty big, and g triple prime gets quite big, right? These things can exist, but they don't have to be small. So it depends whether this is growing faster or slower than k plus 1 factorial. So yeah, don't assume in general that constant is small, because you may get into very deep trouble if you assume that.
So, Professor, going
Yeah.
back to the other process, so if we don't have this condition that the derivative, higher derivative up to k are equal to 0,
Yep.
then our order of convergence is just linear because we got a constant.
That's right.
set to
That's right.
to
So
power.
if we don't assume these higher derivatives are 0, then we're stuck with linear convergence, because when we did here it is, this limit here, we got a constant, and this constant was not 0. It was just something less than 1. So linear is all we get out of that. So for a general convergent fixed point method, all you can assume is linear, unless you do a little more work and check that you have some of these extra conditions.
And it is the first non-zero derivative we get, right?
And it's the first non-zero derivative we get that's going to tell us our order of convergence, exactly.
So if there's just one of them that's not zero,
So if it's just one of them that's not 0,
and the rest is zero.
yeah, then it doesn't matter if, so if G prime is not 0, and then G double prime, G triple prime, and a bunch more are 0 after that, too bad, it doesn't help.
Okay.
Okay, so let's do an example of this. You could probably guess the example. I'm going to do Newton's method, right? We already know Newton's method has quadratic convergence, so we proved that last time. And it was it's I guess not too hard, but it's a little bit of an involved proof. But now we've got a new framework for analyzing Newton's method. We've done the hard work, and we can plug it in here. So let's see what happens. All right, Newton's method. Okay, so remember Newton's method went like this. Xn plus 1 equals xn minus f of xn divided by f prime of xn. Okay, so this is indeed set up as a fixed point iteration, right? Xn plus 1 equals something. All of this is my g. So my g of x is x minus f divided by f prime. Okay, we should do, if we want to establish higher order convergence, or even just analyze this in general using a fixed point approach, we need g prime. So what is g prime? G prime of x is equal to 1 minus, okay? Now we take derivative of this, I get f prime over f prime, and then I'm going to leave this guy fixed. I get 1 over f prime squared times f double prime. Okay, and this simplifies. Oh, I guess I'm assuming I'm in the setting that we want for Newton's method, in that f prime is not 0 at the root. So what do I get? F double prime divided by f prime squared. Okay, so what's g prime of alpha? Okay, you said part of it, yeah. You said the important part of it, in fact. So the important part of it is we've got this f of alpha term, and then we've got these other terms. F of alpha is 0. So we started by assuming alpha is a root of f. That's what we're looking for, right? So if f of alpha is a root of f, so if alpha is a root of f, this part is 0, which makes this part 0.
F prime of alpha can't be 0.
F prime of alpha can't be 0, exactly. So for this to work, what do we need? We need f to have second derivatives, and we certainly need f prime alpha to not be 0 to make this work. And we've seen those conditions before, that Newton's method isn't going to do what we want it to do if f prime alpha is equal to 0. So this isn't a surprising condition that pops out, but it does pop up again. So this works as long as f double prime alpha exists and f prime alpha is non-zero. Right, so again, we see that the first derivative of, when we phrase this as a fixed point iteration, the first derivative is 0. So we expect then order 1 plus 1 convergence, order 2 convergence, quadratic. Okay, so we expect order 2 convergence. So if you wanted to be really clear on that, we should check for the second derivative, absolutely. Right, so we could go ahead and do that. I'm not going to do that calculation now. You're welcome to. But, you know, and then you might be even be able to say, well, under what conditions could a Newton's method converge even faster, right? Just by saying, well, when does G double prime actually equal 0? So I don't know if it's that's as simple as deriving the method. That's just saying if I'm using Newton's method, right, and Newton's method is fixed, Newton's method is this. I could take another derivative of this function and say, well, under some conditions, you know, if the derivatives of the higher derivatives of this are related in the right way, it might be 0, and I might get faster convergence. So, yeah.
So, like, well, I'm thinking of like an example of this, but like, is that why is fixed point iteration in part like made in order to kind of sometimes rectify certain situations where Newton's method kind of fails or it can't work?
Are fixed point methods made to work with settings where Newton's method can't work? Sure. Fixed point methods, you know, fixed point methods include Newton's method, but they include lots of other methods. And indeed, sometimes Newton's method won't work, or it won't work very well, and you need something else. So we talked about for a given root finding problem, there's lots of different ways of rewriting it as a fixed point iteration. Well, you go through and say, I've looked at them. Now let's compute the G primes for the different methods I'm guessing at and say, you know, which one of those keep G prime less than 1? Do any of them make G prime equal to 0? So certainly, you can use different fixed point methods when Newton's method doesn't work well. It gives a nice tool for analyzing these methods, right? Even for like analyzing Newton's method here, when I've got a big framework that just says there's not much to check, I've got to basically check that my G prime is less than 1.
So, Professor, if we go back now at this particular point and mimic the proof we just did,
Yes.
The k up to k derivative equal to 0.
Yes.
So when we use Taylor expansion, we will get an error, a second order error. And we are saying that the derivative, the second derivative should exist. So then we will get the error that is the order that is 2, because at the end of the day we're going to get this error, but the derivative here is going to be up to order k.
Yeah, so if we did this specifically with this function and mimicked this exactly, we would get the second order. Exactly. There's lots of different ways of analyzing the same problem, and you want to use the simplest way usually, right? We've got lots of tools in our toolbox, and there's no point pulling out something more powerful and complicated than we need when we've got now a very simple framework for analyzing things like Newton's method. And really all we'd have to check here, if G prime alpha is, okay, in this case equal to 0, and G prime is continuous, then G prime is going to be less than 1 in a neighborhood of alpha, right? So that satisfies the condition of the fixed point iteration theorem easily. G of alpha is equal to alpha. Its derivative is less than 1 in this window. So it's never going to be steep enough to wander outside the window, right? So with just a very simple check, just checking this function, we kind of get everything that we need to satisfy the conditions of our fixed point theorem. We can also use these error analysis techniques to get error estimates, which are nice. How accurate is my solution? And that's great if you say, I have a tolerance that I need to meet. My error is not allowed to be more than 10 to the minus 3 or 10 to the minus 8 or whatever. Then you might ask, how many iterations should I take? When can I stop? I don't want to iterate longer than I need to because that's a waste of time and resources. But if we have error estimates like this, we can try to guess when we can stop our iteration. So estimating a stopping criteria. Say we're given an error tolerance epsilon. I want my error to be less than epsilon at the end of the day. So I need a way to get, just a crude estimate of, I never know exactly what my error is, right? But I need a way to estimate it. So you typically start by saying, well, how much did the method change? And we do what we always do, write in the method. Actually, let me take this back up a step. Let me write this in terms of the actual errors. So, these are the things we want to estimate, but this is what we actually know. All I can tell you is how much the method changed things from one step to the next. All right, so this we know. We write in our method. So this came from plugging in my old guess. Alpha is a fixed point. And I'll compare it to my old error. Okay, and we do what we usually do here. We do a mean value theorem and say, well, I can estimate all of this in terms of my old error. Okay, and again, I don't know what Cn is. I don't know exactly what this derivative is. We know it should be getting close to G prime of alpha, right? Hopefully you have bounds on what it can be or not be. So I'm gonna write this as an approximately equal to, but certainly you could analyze this more and say, well, I don't know exactly what it is, but maybe I know it has to be between 1 and 2 or something. Hopefully it's not between 1 and 2, actually. That would be bad for convergence. Maybe it's between 1/3 and 1/2 or something. Okay, and now this gives me a way of at least ballparking my error in terms of something maybe I can estimate and something that I know. This is just comparing my previous 2 guesses. Okay, so I could say that the error, xn minus alpha, is kind of ballpark equal to how much the iteration changed divided by G prime alpha minus 1. All right, so then I say, when should I stop? Well, I want the error to be less than epsilon. I never know that exactly, but maybe I stop when this is less than epsilon. Or, I put some bounds on what this could be, and I stop when that's less than epsilon. So let's stop when xn plus 1 minus xn over G prime minus 1 is less than epsilon. Okay, in magnitude. What's the stopping criteria it would give you for Newton's method?
Second derivative. Well, something to do with it.
Okay, so you're trying to complicate it. Let's not complicate it. Let's just look at this. What does this say when?
And negative. Just xn minus.
Just xn plus 1 minus xn, right? So for Newton's method, we said g prime is 0.
Right.
So for Newton's method, we could just look at this and say, actually, the change in x from iteration to iteration, right? X changes a lot from iteration to iteration. Quadratic convergence, we gain accuracy quickly. It means this difference is actually a really good estimate of our actual error. It's not exactly equal to our error, but it's a good estimate. So if this is less than epsilon, we're pretty close to our actual error being less than epsilon. You know, maybe you take one more iteration to be safe, or you say, let's make this less than half epsilon or something like that as a safety factor. But basically, the change in x is a good estimate here of the actual error. Okay, again, if you didn't know g prime alpha was 0, if you just said, I know it's less than or equal to some k, right? That's what we generally did to analyze fixed point methods. And I'd say, well, I use my estimate of this being less than or equal to k to come up with my bound. Any questions on that? Right, so the fixed point framework is nice. It's quite simple, actually, and it gives us a nice way of analyzing really a lot of different methods for root finding problems with very little work. We just did all the work on the board today, and now it's kind of easy to just sit for a particular method and just check the conditions, compute your g primes. Yeah?
What's the difference between like an error estimate and, let's say, relative error?
What's the difference between an error estimate and relative error? So relative error is, the exact relative error is going to be defined as the actual error divided by the size of the quantity you're trying to compute. You never know that exactly in real life, but it's just saying, if I'm looking at things on the scale of a molecule, then a centimeter is huge. But if I'm looking on the scale of a galaxy, then a centimeter is nothing, right? So the relative error just says, is a centimeter big or not big compared to what I'm actually interested in computing? Error estimate says, I don't know exactly what the error is, but here's kind of a ballpark guess at what the error is. And this should have the right order of magnitude, right? The digits will be a little bit wrong, but the order of magnitude is right here. It's a good estimate.
Professor, for the implementation, let's say, of Newton methods, it's not that complicated to get a loop and do all that with a number of reactions. But then a good algorithm will also include the stopping condition.
A good algorithm for Newton's method will certainly include the stopping condition, yeah. So you're right, it's not hard to say, okay, for j equals 1 to 10, do this. What you would instead want maybe to build in is, while my error is bigger than epsilon, I do this, and at each iteration now I update what do I think my error is. So, it is one extra line in your code, but it's one extra line that could make a big difference.
I see. So we are given the error, but we can also update the error.
Given the error, but you can update it exactly, or you update your estimate of the error at every step.